At HQS, we have developed the Struqture library to create, store and exchange spin Hamiltonians for quantum advantage use cases. In this video, we show how one can construct and store a spin Hamiltonian in Struqture. Let us have a look at the example of a Hamiltonian for 4 spins. When we write down the Hamiltonian on a piece of paper, we write it as a sum over single spin terms and interactions between 2 or more spins. All terms in the spin Hamiltonian can be described by products of standard Pauli operators x, y, and z. A single spin or simple cubic term is defined by a single Pauli operator acting on one spin, for example z on spin 0 or x on spin 1. A 2-spin term is defined by a pair of Pauli operators, for example a product of x and x coupling spin 0 and 1 or z and z coupling spins 2 and 3. To act as an input for quantum algorithms, the spin Hamiltonians need to be constructed on a computer. For classical simulations, spin Hamiltonians are often constructed as a matrix in a computational basis. For the previous example of 4 spins, this gives a 16 by 16 matrix. At 4 spins, this representation is already unwieldy, and constructing it like this only gets harder with more spins. More importantly, even in a sparse representation, where only the non-zero elements are stored, we will run out of memory storing a Hamiltonian in this form for the numbers of spins that can give a quantum advantage. For this reason, it makes more sense to construct and store spin Hamiltonians on a computer the same way as when writing it down for units. We start from the Hamiltonian written as a sum. Each product of Pauli operators in the sum can be written as a string of spin index and the operator on this index. Each spin index not appearing in the string does not interact and corresponds to the identity operator. By identifying absent terms with identity, we arrive at a very compact way to write down the Hamiltonian in a few lines of Python code, and it takes up very little memory on the computer. This symbolic way to store spin Hamiltonians is well suited as an input for quantum algorithms in quantum advantage use cases. If you got interested in Struqture, it is available as open source, and you can have a look at our Struqture library on